Okay, so we're a minute past 2 o'clock Eastern, so we'll get this going. Good afternoon. My name is Nick Leone. I'm a project engineer at America Makes. Today I'm going to be hosting our America Makes TRX webinar. A little background on the webinar series before I introduce our speaker. The America Makes Technical Review and Exchange webinar series was created to assist America Makes in our mission to expand and accelerate the footprint of additive manufacturing and 3D printing. This platform provides an opportunity for members of the additive manufacturing and 3D printing community to come together and share knowledge and experience with the broader community. If you or your team are interested in presenting a TRX webinar, you can contact the webinar series administrator, Jason Thomas. You can reach him directly at jason.thomas@ncdmm.org. One more note before we kick off the talk. At the end of the presentation, there will be a question and answer session. If you have any questions as the presentation progresses, please submit it in the Q&A space on your WebEx screen, and we will ask it during the Q&A session. We'll do our best to get all of those questions answered. So today's webinar is a holistic approach to performance evaluation of AM melt pool monitoring systems, and it will be presented by Dr. J.S. Jain of Baker Hughes. J.S. is the digital and machine learning leader at Baker Hughes Enterprise Additive Manufacturing Unit. In his current role, he leads process control and inspection activities, applying physics, analytics, and AI for enhanced quality and productivity of 3D printing. In his 13 years at Baker Hughes, he's led several key R&D projects that received both internal and external recognition. The project he's going to talk about today was awarded through one of America Makes Rapid Innovation Calls. Here to say a few words about that is Dr. Brandon Lane of NIST, who was our government advisor for this project. Brandon?
Right, thank you very much for the introduction, Nick. Yeah, I wanted to thank America Makes and Jesh for letting me be a part of this. This is a proposed project, as Nick mentioned, is of the Rapid Innovation Call. So the background in this project really came from two places. So first, for those familiar with additive manufacturing in situ process monitoring techniques, you know there are a set of relatively similar technologies like melt pool monitoring, layer imaging, etc. For example, for powder bed fusion. And these are starting to appear as commercial products on commercial machines. So despite the prevalence of these systems and availability, there's still a little bit of a gap between their prevalent availability and then their widespread application and use in an industrial setting. So the second reason is we've seen the value and impact from use of test artifacts and methods, primarily stemming from like development of the NIST AM test artifact and artifacts that were designed for part of the ASTM ISO standard 52902 for assessing geometric capabilities. So the main questions that I was hoping to pose with this project is can we identify some basic methods, including test artifact design, on-machine test steps, post-fabrication measurement, and data and results analyses that can help industrial users characterize things like repeatability or reproducibility of the monitoring systems, establish baseline or ground truth values, or determine relative sensitivity to local geometry, anomalies, etc. So hopefully this project inspires some further R&D in the direction of developing some clear, practical, and maybe someday standard test methods for characterizing in-process monitoring technologies. Thanks, Nick.
Thank you, Brandon. So without further ado, Jayesh, take us away.
Okay. Well, thank you very much for that introduction, Nick, and thank you, Brandon, for the background. So let me go ahead and get into today's topic. But before we do that, I would like to first acknowledge all the contributors. You already saw Nick Leon. He has been very helpful, given that this was one of our first projects with America Makes. He really guided us through the process and made it, easier for us to focus on the execution of the project. So thank you, Nick. And of course, Brandon, for your constant feedback and technical insights. I would like to also acknowledge Baker Hughes' leadership because this was a rapid innovation call, very fast-paced project, and they really prioritized this one and also added a lot of cost share. And then finally, all the contributors to this project, the project team. As a lead, I was happy to have a great team of subject matter experts. Again, given the time frame, we did not have much scope for iterations, and therefore it was important to have a diverse set of expertise that you see here, from process, design, analytics, data engineering, CT scanning. So all the results that I'm presenting today are a result of great teamwork. So thanks to the team. So with that, essentially, we are going to, I'll give an overview of the project and the technical approach that we took. And then we'll spend majority of time through the demonstration of the developed test artifacts and protocols. I would like to mention that today we'll demonstrate the test on two different systems, commercial systems, melt-pool monitoring specifically. But I would like to emphasize that we won't disclose the names, and we encourage you not to interpret these results as endorsement or disapproval of any commercial product. The focus was developing tests that would be easier to adapt, and like Brandon said, this could lead to best accepted best methods or standard methods, but I think some more work will be needed there. Okay, so just to summarize, this project was in response to a rapid innovation call last year, and the source of funding was AFRL. The particular topic was development of test artifacts for characterization of in-process monitoring systems, like Brandon said. This project aligned with two different swim lanes within technology roadmap of America Mix, and multiple CTEs among those. The duration of the project was about 4 months, actually 4 months, with 3 months of execution and 1 month of iteration and reporting. The amount of funding was $65,000 from America Mix and AFRL, and Baker Hughes added a cost share of $29,000. So with that, let me again refresh that this particular, the main driver for this project was the time and effort that typically are spent to realize the true capabilities and limitations of complex systems like melt-pool monitoring. And therefore, the objective was to develop artifacts, but not just artifacts, also protocols, as you will see, for evaluating melt-pool monitoring systems in particular. And like earlier we said, the expected outcome or benefit is that this could lead to a standard method that not only the vendors of those systems and users, but also the designers of those systems could use. And let me give a brief background about artifacts, because we did mention geometry and NIST artifacts. NIST artifacts work very well for evaluating the machine or process performance. One of the things that we had noticed before we started this project was that the geometry alone is not enough for evaluating the melt-pool monitoring systems, and particularly because a lot of defects or situations lead they are caused by not just geometry, but rather several other factors that go on during the AM process. And we had an encounter like that earlier before this project started. We had evaluated our own, I mean, not our own, but the ML pool monitoring system that we have um, using designed defects, where it's more geometry based approach, where you will see that we and design certain small geometries or features to mimic defects, and the system had passed that test. They were able to detect it, but then when we encountered another type of defect, particularly lack of fusion defect, the system did not pick that up, and we then realized that there were some issues with the hardware that needed to be addressed. The point being, we realized early on that geometry alone would not be enough, and therefore the technical approach that we took was, I hope you are able to see the slides that I'm moving. I'm assuming that, so if you're not, let me know. We are on slide 7. We took an approach to where we created different types of situations and defects to evaluate different aspects of the Melbourne monitoring system. As you will see during the presentation, we developed 12 different types of tests, or rather we probed response along 12 different aspects of the system. The tests are categorized into 2 levels of complexity. So level 1 tests are essentially you run the test, collect the data, and then just evaluate it. Versus level 2 tests require either CT scanning or special, kind of hardware or something that is not as easy as just running a test, a typical print. Further, overall, the tests are categorized into 4 types, and we will go through each of those in detail. However, at high level, the full plate weld test essentially prints on the entire build plate, and to probe certain aspects such as position dependency, sensitivity, repeatability, and so on, as you will see in the table here. The geometric features test was aimed at testing sensitivity to features, including overhang, size, orientation, converging structures. Now, I will say it upfront that we did not do all of these features. We did one of the most interesting features and most challenging features, that is shrink line, and I will go into detail of those. But the other features, we think that more work is needed, particularly some benchmark solutions would be needed for additional features. Within the level 2 tests, there were 2 types of tests done. One is designed defects that I alluded to earlier, where we create known small geometries to mimic defects and then attempt to detect those using the Melbourne monitoring. And the last one was one of the most interesting and novel, I would say, setup tests, where defects are induced by altering the parameters in certain manner, and we'll see how. So all of these tests are essentially artifacts are consolidated on a single build plate. Now, majority of tests you could do just with one print, and some require some adjustment that would be done in a separate print. So as you will see that some of these tests, particularly full plate weld test and design defect test, these are aimed at addressing how the systems are being used today in a typical production setting where once you define the setup, you don't make significant changes to it as long as your volume is significantly high. But then the other tests like induced defects and geometric features are tests designed to really push the limits of multiple monitoring systems. And you may see that, they are somewhat challenging for the current systems. But the hope is that either the interpretation techniques or the systems themselves will advance and meet those test requirements. So with that, let me start going through those tests in more details, and we will start with the full plate weld test. So here is an overview of the full plate weld test. Essentially, in this test, the printing is done on the entire build plate. And what you see is all the artifacts on this particular build plate, but what you see are the entire build plate actually has a few layers that are printed. You also see that it's rather unclean, not so clean, and the reason being we are trying to induce defects, and you will see a lot of dark spots here and there. But so let me go through the test itself. So within this test, first working plane is established by printing smoothing layers, and you could print one, two, or a few until a working plane is established. Typically 2 or 3 layers are enough. But then the real full plate weld test has essentially 2 types of layers. First layer is uniform layers, and there are 3 identical layers printed. And when I say identical, they are identical except in the stitching zone. Particularly, this was a dual laser system, and therefore stitching zone may have differences from one layer to another, but rest of it was identical with constant parameters. So constant parameters throughout the plate. And the second type of layer, a single layer, is printed on top of it. It has 64 small regions. Those are made up of 8 unique parameter combinations repeated 4 times for each laser. That's how we make up 64, and you will see more details in upcoming slides. And essentially these 4 layers together is the core of the test, and then this is repeated at reduced gas flow with substantially reduced gas flow to cause improper delivery of laser power. It's kind of induced defect. And then lastly, a double exposure test is run where the laser is exposed without recoating. And this particular test is run to evaluate the sensitivity of the multiple monitoring systems to presence of a powder layer. Ideally, we would like to do a short spread test as well. However, the systems, for good reasons, are designed such a way that short spread is not consistently created. It has inbuilt safety systems, and therefore double exposure test kind of serves a purpose to evaluate that sensitivity to presence of powder layer. So these tests were demonstrated on 2 different multiple monitoring systems, System A and System B. System A used alloy 718 as a material, and System B had Ti64. Both of these systems used photodiodes, slightly different number of photodiodes, but all of them were coaxial with similar field of view, and sampling rates were high enough, more than 50 kilohertz, System A provided two metrics. System B provided one metric, although you could split that into two metrics as well. Um, um, the image, the data that we worked on were essentially 100 by 100 micron bins or pixels, that type of image coming out of it, rather than the time series data. And like I said earlier, the objective of these tests was to be able to make it as simple as we can, as fast as we can, but also not only on the running the test itself, but also on the interpretation side. Ideally, we would have liked to use just the interpretation that comes with multiple monitoring systems, but we don't think all systems are there yet, and particularly for tests that were designed here, they could may be able to do it for a production setting, but the specific test here done here, not all systems could provide interpretation. And therefore, on the interpretation side, we used metrics that are used by these systems typically, like statistics such as mean, median, min, max, standard deviation, things like that, rather than trying to come up with a new interpretation technique, which was not the goal or scope of this project. Okay, so with that, let me get into some of the results from this test. So this slide shows results from the uniform layers. So the three uniform layers that were printed under normal conditions. So each test creates or uses a ground truth, and in this case, ground truth or a reference. And in this case, reference was the laser power verification that is not shown here, but so that we kind of had a verification done on how much power is being delivered. And also post-exposure images serve as sanity check on what was printed. So the way these uniform layers are evaluated is a reference is established as a median within that layer for a given laser. And then we did notice that some of these systems had reflections or hotspots directly beneath the laser, and therefore we had to treat that differently. We masked to remove it, and then calculated a deviation from the mean within that laser for that laser, and just use discrete beans to just average it. And what you can see here is the plots at the bottom show mean deviation or mean absolute deviation. So mean deviation is just a difference from the mean. That it shows that there are the hot spot near below the laser, but then values are generally lower surrounding that hot spot, and then they are higher closer to the right and left edges. Now, what that means is, although we printed with uniform parameters, we are seeing differences in the multiple monitoring metric. Now, is it real or is it a noise? And so our laser power verification served as a reference here, and therefore we knew that this is not coming from the laser itself. And what that means is this is a noise in the measurement system. And the noise could be from the reflections from within the chamber, beam splitter, or whatever hardware. Okay. And what you see in the line plot here on the left is those are shown for the 3 layers. All 3 layers were printed identically, and if you took a vertical section through the plate, you see that the one on the left, that's for the bottom laser, the 3 lines, and then for the top laser, the 3 lines. The first layer shows much higher noise, and that could be because just after establishing the working plane, there could be some more noise. But then second and third layer stabilize and show the amount of noise that exists. So this shows us the position dependency. Okay. Then moving on to the essentially next layer, which was a sensitivity layer. And like I said, there were 64 regions that are shown here. They were strategically designed to have 4 repeats per laser, and also scattered, so that the dependency on position, that factor could be also evaluated. And so the way this was analyzed was for each region, if we were to compare it with any other region among those 64, a metric called Jensen-Shannon divergence was calculated. Now, the name might seem intimidating, but it's a statistical measure for similarity or differences between 2 distributions. So we are not just taking an average within a region, we are taking all the data points and comparing the distributions. This is bounded between 0 and 1, and what you will see in the next slide how we interpret it. So here is a plot that is made here to present it in a condensed manner, and I will go back on the earlier slide in a moment, but essentially what you see is the 64 regions, the data from it is plotted as a heat map. In this chart, what you see is the top, so they are plotted against each other, and the color means the darker means the 2 regions behave very similarly in the measurements, and if the lighter means they are very different. Now, going back, the parameters that were used in these 8 unique combinations had power, speed, hash distance combinations that were different. And then if you look at the volumetric energy density, it was varying like this. And the way this plot was created was these regions were arranged by their increasing volumetric energy density, or VED. What that means is, now if you look at this green square here, it essentially compares a set of 4 squares with each other. And these 4 squares have identical parameters, because this is for laser 1 and the bottom right is for laser 2. So for laser 1, those 4 have identical parameters. So they should all be ideally completely dark, meaning they should have identical measurements. And so that's how you can compare. If they're lighter, that means they are not completely identical, but since they're very dark, they're very close. Now you could then compare 2 different VEDs by looking at the diagonal term here for these 2 sets of squares that have very different VED, and the light color means different VEDs were separated very clearly in the measurements. You could use the same technique to compare 2 lasers. So if you look at the same sets of those 4 regions with identical parameters, one printed for laser 1 and another for 2, the cross term there tells us how similar those 2 sets of squares showed up in the multiple monitoring measurements. And what you see is the color is not completely dark. So they don't look like they're same in these measurements. So that tells us that for some reason, the multiple monitoring leads to different values for the two lasers. From the reference that we had, we knew that the two lasers are not delivering different powers. They're delivering very similar or same power, and therefore this lack of similarities attributed to some calibration within the multiple monitoring. What that means is you cannot simply take measurement from laser 1 and 2 and compare them and tell that, okay, laser 1 is delivering lower power or higher power, because the multiple monitoring itself has slightly different calibration here. So that's an easy interpretation. And so this plot provides a lot of information in a condensed manner. So we conducted the same tests 3 times over a period of 2 months to see how repeatable the system, both the AM machine itself, but also the monitoring system are. And what you can see is they were very similar. This could be more quantified, but this it was a good confirmation. So now moving on to the reduced gas flow test. This was the same full plate weld cut test conducted as at lower gas flow, and you see these two post-exposure photographs. One shows the reference layer, and you see the effects of camera lighting there. So dark and light spots are they're supposed to be uniform. And the one on the right shows with reduced gas flow how it resulted in improper, lack of fusion or improper welding. Now, the way this is analyzed is the reduced gas flow layer is compared with the reference layer or with the normal print, and the differences are calculated in the metric, and they could be presented point-wise or in those discrete beans. But essentially, once we apply a threshold of, say, the level of noise, you can see what portions are showing up as defective. And in this case, you can see it picks up about 60 to 70% of the actual defective regions. So, and rest is not picked up, likely because of the noise that we saw earlier. And so that gives a good way to evaluate how gas flow effects could be picked up. Similarly, the last layer, double exposure, was printed, and what you see here is compared with a reference layer with powder layer, and this is without any powder layer. The difference is consistent, and you can notice it. And so therefore, you can say that it is able to show the differences, but if you look closely, the magnitude of the difference is of the same order of, as the noise itself that we saw earlier. What that means is the entire layer here was missing, but if only pockets have smaller layer thickness, then it is of the order of noise, and therefore this is not very sensitive to powder layer thickness, which was somewhat surprising. But what would be helpful to have here is kind of a benchmark or theoretical solution to tell us how much difference to expect here. Okay. One more test that was done was essentially optical system anomalies, and in this case, defects on the lens. So this was level 2 test because we had to use this lens that had burn marks on it, and so we had to install that and conduct the same full plate weld test, and then use a normal print as a reference, and then again go through the similar process of calculating the differences. And what you see here are several hotspots show up, but these are 4 layers, and what you see is in all 4 layers these 2 spots are consistent, and they correspond to the defect on the lens. And what that means is others could be gas flow or some other noise, but these two consistent spots were detectable, which means that the system was able to detect those tiny defects on the lens. So overall, full plate Weld tests told us the location dependency, the sensitivity, repeatability, and essentially how the system is able to catch things that are related to delivery of the laser power to the powder bed. Okay, so with that, we will now go through the rest of the tests. Geometric features test, particularly a special test was developed here. In this case, the geometry was designed such a way that it leads to thermal distortions that show up as upsets on the surface of the part itself. And this may be called in with different names in different parts of the industry, but we accentuated that effect by designing this special converging structure and the curve. And what you see here, denoted by arrows, is an upset in the top few, just few layers below the top layer. And that is due to the thermal distortion occurring when two columns here converge. And we knew that this was a particularly challenging defect for a system to detect. However, we put it out as a challenge, and not to our surprise, we did not see any indications within the multiple monitoring data to indicate that this particular layer had any different signature that would stand out. And therefore, the system essentially did not pass this test. We would have liked to do more features, but we think that the lack of benchmark solutions or theoretical solutions kind of became a hurdle here for size orientation type of effects. Now let's move on to the design defect test, where like I said earlier, we designed these small features. What you see in this cylinder here are spherical features of increasing diameter, and then 3 sets of cylindrical features with increasing diameter. Those were designed, and what that means is the laser wouldn't print any material there. And then we printed it and then conducted a CT scanning to detect where those defects existed, or the features rather, that appear as pores. And we were able to see, taking a closer look on this slide, here the x-axis is the height of the cylinder and y-axis is radius from the center. So first 3 sets here are supposed to be spherical defects, and then last 3 sets cylindrical. And what you see here is the smallest of the spherical features were not detected or not printed per the CT scan, which was our ground truth, and rest of them were printed. The multiple monitoring with this plot shows anomalies at all 6 of those locations. And so what that means is it would suggest that there were defects printed even, or defects or features, whatever you call it, even at the smallest sphere size. What is not known is whether they were printed and then cured by the subsequent layers, that which happens in 3D printing. But in either case, the multiple monitoring could not tell us whether they were printed or not, or they were cured or not. The one thing to notice here is this particular test, typically is successful because the laser does not deliver any energy in the regions where features are designed. And therefore, a multiple monitoring system, as we saw earlier, responds very well to energy delivery. And therefore, it typically performs well, but that does not guarantee that it is sensitive enough. So with that, let's go to the last category of defects, which is induced defects. This was planned in a new way, and let me explain how it was planned and conducted. So the objective here was to traverse the process map. This is the laser power versus scan speed, and try to induce defects in different regions. One particular thing to pay attention to is, like we said earlier, the energy delivery, the system responds well to energy delivery, but what if the volumetric energy density is constant, and then defect appears in one case and doesn't appear in another case? Is the system able to capture that scenario? And therefore, the lines you see here that are pointing towards the origin are constant energy density lines. And so each of these 6 types of specimens had a different parameter combination. So the first specimen was baseline, so good printing parameters shown by this point here, and then 7 segments, all of them having constant parameters. Then each of the other specimens had different parameter combinations in each of those 7 segments. Each of them had one segment that was baseline, and other segments had some kind of a variation. So specimen T and U had constant VED at low, medium, and high levels, represented by those 3 lines here, which is accomplished by changing scan speed and power. And then the other 3 had variations in head spacing, speed, and power. And all of these were printed and CT scanning was done. And what you see here in this plot, the color map shows detected pore sizes. These are the sizes are the largest size for a connected pore, and only sizes more than 100 micron are shown here. And you can quickly see that baseline did not have maybe only one pore detected, which tells it was a good printing parameter. And then each of the other specimens show up defects as we enter into lack of fusion or keyholing regions, different defect regions. For example, specimen U has low energy density in the first 5 segments that corresponds to this line, and you can see that at the lowest of the parameter combinations near the lack of fusion defect, you can see a lot of pores appearing. So this served as a very good ground truth, very successful way of creating these defects in a controlled manner. Now the question is the multiple monitoring system able to show indications of these defects? And the 2 metrics from this system A were plotted, and like I said earlier, the typical metrics such as median, standard deviation, and minimum maximum values, all those were plotted and looked at, and particularly for cases where we knew the defects appeared. So first is baseline, then second, these first 5 segments have constant VEDs, and then for example here these first 5 segments have low energy density, and the defects appear in the 5th segment, but the monitoring system response does not show any indications that defect appeared in the 5th one. It does show some drop here in the 2nd segment, which did not correlate with any defects, and therefore we did not see any remarkable indications of presence or absence of defects, and for a constant VED cases. Looking at the head spacing, as the head spacing was increased, made wider, we expected defects to appear, and they did appear at the top few segments. Looking at the Melpool monitoring data, the median dropped because the overall energy density reduces. The standard deviation increased, and but same type of behavior did not correlate with defects for the speed case, where standard deviation was higher for segments where defect was absent, and therefore no consistent indication correlated with defects across these specimens. Similar situation with a second metric that was used, and I would not go into details, but we did not find strong correlation with the defects. Remember that these parameters are changing here. This is not a typical production setting, so this is more challenging test, which would be helpful in low volume production or even parameter development. And therefore, the aim is to just push the systems towards this. One more type of evaluation that was done was data processing artifacts. Essentially, the images or data that are produced out of the systems can have some out of bound values or filtering effects. For example, hatch spacing led to some zero values in the bins because the bins were too small, or hatch spacing was too large. And filtering provided by some of these systems is helpful to some extent, but this is something to be aware of. And sometimes the sensors saturate and the values exceed the maximum range. So with that, I would like to just summarize that we were able to develop basic as well as advanced tests for evaluating the systems for the purpose of today's production setting, as well as what we think as future potential for Melpool monitoring systems. Specifically, the system A that was demonstrated here demonstrated very good sensitivity to the energy delivered to the bed. So anything that leads to lower or higher energy delivered and associated anomalies were picked up. But then the porosity due to parameter variations outside of typical constant settings was not detectable. So with that, I would like to just thank everyone for paying attention and open the floor for questions.
Thank you, Jayesh. Very interesting. We do have a few questions. One of them is, how were the seeded defects formed in the coupons? I believe this was the design defects test is when that one popped up.
Right. Okay. So in this case, the features were designed in the sense that if we put say 200 micron diameter sphere the slices are the scan pattern on those slices. We had to make sure that the laser actually uh, does not print in that region, because some of these sliding softwares have inbuilt preventive measures for good reasons that prevent very tiny features. They just patch it up. We had to make sure that that hasn't happened. And secondly, we have to make sure that the hatch spacing and the features don't interfere such a way that the features are printed even though you don't want to, well, material is printed even though you don't want to print it there. So that's how they were designed essentially. And these are available to the America Makes members, and as long as this is provided in CLI format, so you could download and look it up how it is done. But it's done.
Okay.
Does it answer the question?
I hope so. If not, the gentleman who asked can maybe post a follow-up. Another question, for the full plate weld test, how did you account for the variability or location dependency of the actual power delivered by the lasers? Also, were the two lasers delivering identical power?
Good question. So for each test, we had some type of reference or ground truth. In this case, for the laser power, we needed to make sure that the laser power, we knew how much it was delivering. And so I think most of the printing services, they perform some kind of laser power verification, and I'm showing results of the verification that we perform. And what is plotted here is the XY, which is the plate XY coordinates, and the Z here is the measured power, and the color bar and the size shows you how much it deviated from what was intended. So this verification was done at 4 different power levels. And what you see this is done for the 2 lasers. And so left plot shows you the deviation was slightly higher in the middle right portion versus on the right, the deviation was slightly higher at lower power level, and then you can see where those were. But overall, all of these deviations were less than 0.5% in most of the cases, and therefore, and from one another also. So the difference was much lower than what would cause position dependency in multiple monitoring systems. So that's how, yeah, okay.
There's a question just added about, did you draw conclusions about the multiple monitoring system B? We looked at A through
Right.
most of these slides, but did you how did B
That's
look,
true.
basically?
Right. So yeah, for the limitations of the time we have, I did not present the results for B, but essentially we noticed similar situations like the sensitivity to the position dependency, for example. Let me show you, for example, this is position dependency for system B. And what was seen here was the position dependency was not as constant or consistent as we see with system A. Okay, there was noise, but noise has some variation. Another thing we noticed, this was noticed with both systems. So this is a metric for system B, and these systems provide different types of metrics, right? So with system A as well as with system B, we saw some inconsistencies depending on what metric we are looking at. So for system A, one metric showed very good sensitivity, but second metric did not show very good sensitivity. And system B, this particular metric did not show very good sensitivity. The detection of reduced gas flow was very good with system B, slightly better than system A, right? So, um, and so on. Same with double exposure. So, very similar, consistent difference, but it was of the order of, I would say not very sensitive. And therefore, benchmark solution here will tell us, why both of these systems turn out to be not so sensitive to presence of powder layer. So yeah, those are the results for system B very quickly.
I guess I'd like to.
What was good to see was that we performed these tests with very minimal to no changes, and that was our point, was whether the test is able to evaluate a completely different system, different material, with similar protocols, and it was good to see that it was.
I'd like to add too to that the high-level results for System B are also in the final report that will be available to America Makes members in the digital storefront and hopefully the not too distant future. I believe that was in one of the appendices to that report. I think we have a chance just for one last question, and I would ask the question I'll pick here is which of the tests do you think provides the most practical value in terms of performance characterization of the process monitoring instruments?
Very good question. So I would look at these four categories and say that, like I said earlier, some of these tests are aimed at addressing today's challenges, and then some for tomorrow's challenges. And if you were to pick today, I would pick the ones that address today's challenges, particularly the full plate weld test, which queries along several different aspects. It would be my favorite one. And then for sanity checks, you could do design defects tests. What I would like to also have done was the overhangs and size and orientation, for which I would really like to have some benchmark cases, which I think we lack in AM community in general. That would be a nice one to add to the list.
So maybe a future America Makes project for that one, huh?
Well, benchmarks focused on benchmark solutions and problems and solutions would be very nice to have. It would not only serve this, but also maybe verifying simulations, for example.
Understood. So we are up against 3 o'clock here, so we're going to wrap this up. Unfortunately, we didn't get to all of the questions, but we're out of time. So I would like to thank Jayesh and Brandon for their time and effort. If you have any further questions for Jayesh, please reach out to him directly at jayesh.jain@bakerhughes.com or to me at nick.leone@ncdmm.org. A recording of this presentation will be available on the America Makes YouTube channel, and a copy of these slides, as well as the final report and deliverables for this project, will be available in the America Makes digital storefront in the not too distant future. Please reach out to me, Nick Leone again, if you have any trouble accessing it. Our next TRX webinar will be on February 23rd, 2022 from 2 to 3 p.m. Eastern Time, and it's presented by America Makes member Altair as they highlight their Inspire software in a talk called DFAM with Inspire, Don't Be Late to Lightweight. Please join us for that. The registration link will be up shortly on our website if it isn't there already. Just a final reminder, if you think you or your organization would be interested in sharing on this webinar series, please reach out to Jason Thomas at jason.thomas@ncdmm.org. Thank you again to Jayesh. It was an excellent presentation. We appreciate it. And thank you to all of you for joining us. Happy New Year. See you next time.
Thank you, Nick, and thank you for the attention.
Have a good day, everyone.
Have a good day. Bye.